Hello everyone. Welcome to the PTN Multimedia Classroom. Let's go over the basics of MPLS technology. First, let's look at the basics of hop-by-hop IP forwarding without MPLS. How is a packet destined for the IP address 47.1.1.1 forwarded over IP routes? Each router stores a routing table. This table contains information about a path to a specific network terminal. When a router receives an IP data packet, it looks the IP address up in its local routing table and bit-by-bit searches for a matching entry mapped to the destination IP address. Ultimately, it finds the entry that is the longest match. This is how the longest match rule works. Let's simulate a route lookup process with the IP longest match rule. First, we list a data packet's destination IP address and the route entries contained in the routing table in binary. Next, we match the destination IP address against each route entry byte by byte from left to right. We find that route entry 1 does not match the destination IP address, so we ignore it and continue our analysis. Route entry 2 is also a mismatch. We ignore it. This means that route entry 3 is the longest matching one. Route entry 3 is mapped to outbound interface 2. This determines the next hop of the packet. From this process, we can see that the longest match rule is used to look up routes byte by byte. This method is slow and inefficient. Now, let's move on to the process of forwarding packets on an MPLS network. In MPLS label forwarding, labels are assigned to nodes to establish express paths for packets. Along these paths, each time a packet arrives at a device, the device merely swaps the packet's label without the need for route lookup. Next, we will simulate the label switching process from the time a packet enters an MPLS network to the time it leaves. When the packet leaves the first device, the packet carries label 50. After it reaches the second device swaps label 50 for label 40. The packet with label 40 leaves the second device and reaches the third device. The device removes the MPLS label before the packet leaves the node. This process shows that the MPLS label switching technique is very fast and efficient. This is because the IP header in each packet does not need to be analyzed by any hops on the MPLS network except the network edge nodes, making MPLS forwarding much faster than traditional IP forwarding. However, MPLS does more than just quickly switching and routing packets. MPLS is short for multi-protocol label switching. Label switching has just been described. Now, let's learn about multi-protocol. Multi-protocol means not only that MPLS supports various types of network layer protocols, but also that it is compatible with various data link layer protocols. In the 7-layer OSI model, the network layer is layer 3, and the data link layer is layer 2. Being compatible with both layers, MPLS is positioned at layer 2.5. This allows MPLS to combine the advantages of both layers. Just as two heads are better than one, MPLS has the advantages of both layer 2 and 3. From this point of view, we can say MPLS wins. Before we learn about MPLS technology, let's take a look at some of its basic concepts. The first concept we will discuss is the MPLS label. Packets enter the MPLS network. The format of a packet is shown here. As you can see, the MPLS header is between the layer 2 header and layer 3 IP header at layer 2.5. Okay, let's analyze the structure of the MPLS header. The label is 20 bits long. The number of label values is 20 to the power of 2. That's over 1 million. Labels 0 to 15 are reserved for special use. A label is a short identifier of a fixed length. It has only local significance. The label uniquely identifies a packet forwarding equivalence class, or FEC. The EXP field is 3 bits. It is reserved for experimental use and for setting priorities. The 1-bit S field identifies the label stack bottom. Value 1 indicates that the label is at the stack bottom. Theoretically, MPLS labels can be nested indefinitely. The TTL field indicates a time to live. Each time a packet passes through a hop, the TTL value decrements by 1. When the TTL value decrements to 0, the packet is dropped. In most cases, each packet is assigned 2 labels on the MPLS network. The inner label identifies a pseudo wire, or PW. The pseudo wire is a channel directly connecting to provider edges, PEs. Pseudo wires are separated from each other and transparently transmit user services on the packet-switched network. The outer label identifies an MPLS tunnel between the local and remote PEs. The MPLS tunnel carries pseudo wires. An MPLS tunnel can carry multiple pseudo wires. PWs carry layer 2 services, and the MPLS tunnels provide paths for the pseudo wires. A pseudo wire is bidirectional. A tunnel can be either unidirectional or bidirectional. As mentioned previously, a label uniquely identifies the forwarding equivalence class, or FEC, to which packets belong. FEC is an important concept in MPLS. FECs are used to equally treat sets of data packets during forwarding. The entrance router on the MPLS network classifies packets. It assigns packets with the same forwarding pattern to a FEC. This forwarding mode can be likened to a delivery service. For instance, various items are packaged in New York and sent to different destinations. When the packages reach an international logistics company, the company does not check what each package contains. The company simply delivers the packages to their destinations. This processing mode is similar to FEC processing in MPLS. MPLS nodes do not care about the contents of each packet. Instead, they simply classify packets based on the destination IP address, destination port number, source IP address, and source port. As mentioned previously, the 8-bit TTL in an MPLS header has the same meaning as the TTL field in an IP header. MPLS TTL processing helps prevent loops and implements traceroute. There are 2 MPLS TTL processing modes, uniform and pipe. The default mode is uniform. In uniform mode, after receiving an IP packet, the ingress decrements the IP TTL value by 1 and duplicates it to the MPLS TTL field. The MPLS TTL decrements by 1 at each transit node on the MPLS network. The IP TTL remains the same. The egress decrements the MPLS TTL by 1, duplicates it to the IP TTL field, and removes the MPLS TTL. In MPLS VPN applications, to protect VPN services, the structure of the MPLS backbone network must remain hidden. In this case, the pipe mode is used on the ingress. In pipe mode, the ingress decrements the IP TTL value by 1 and keeps the MPLS TTL field fixed at 255. The egress removes the MPLS TTL and decrements the IP TTL by 1. The egress decrements the IP TTL value by 1. When the IP packet is traveling through the MPLS network, its IP TTL value decrements by 1 only on the ingress and egress, regardless of how many hops it passes through. MPLS networks use label-switched paths, or LSPs. A FEC data flow is assigned a label at each node. Data is forwarded based on the labels and passes through the LSP. On an LSP, the first node is called the ingress, the last node is called the egress, and the nodes in between are called transit nodes. An LSR is the core router on an MPLS network. It switches and distributes labels. An LER sits on the edge of the MPLS network. When traffic enters an MPLS network, the LER assigns packets to FECs and requests labels for the FECs. It classifies traffic, performs label mapping, and implements penultimate hop popping for labels. That's all for today. If you want to learn more about MPLS and Huawei products, please see our product documentation at http://support.huawei.com. or contact Huawei engineers.